Calculus can be pretty difficult, but most of the time things make sense. It's not too difficult to differentiate from first principles or derive the product or chain rule, for example. But there's this one really weird rule that looks like a rookie mistake. It's called L'Hopital's rule and says that in some cases, f of x over g of x is equal to f prime of x over g prime of x. And I call this a rookie mistake because differentiation isn't an operation where you can do it to the numerator and denominator of a fraction and end up with the same answer. It's not like tripling or halving both sides. So why does it suddenly work here? Well, to explain that, I need to elaborate on what I mean by some cases. What L'Hopital's rule actually says is that if you take two functions, f of x and g of x, which are both differentiable on an interval containing a, and f of a equals g of a equals 0, or f of a equals plus or minus infinity and g of a equals plus or minus infinity, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x, provided this limit exists. Essentially, it allows us to evaluate limits in those cases where it doesn't look like it should be possible. Cool, but how do you prove it? Well, there's actually a lot of things you have to prove first. Now those first two are kind of boring and basic. The boundedness theorem just says that if a function is continuous on an interval, then it's also bounded on that interval, i.e. there exists an m such that f of x is less than m for all x on the open interval from a to b, and that there exists some n such that f of x is more than n for all x in the open interval from a to b. This can then be used to prove the extreme value theorem, which says that on this open interval, there exists a maximum and a minimum. That's literally all it says. It doesn't tell you how or where to find these values, and it's really just a formalization of the blindingly obvious. Then with that we can prove Rolle's theorem. Rolle's theorem says that if f is continuous and differentiable on the interval ab, and f of a equals f of b equals 0, then there exists some c in that interval where f prime of c is equal to 0. And this is pretty obvious as well. Basically, to get from here to here you have to have some point where the tangent is flat. But despite its obviousness, we can throw together a little proof. There's a chance that f of x equals 0 for all x in the interval, in which case f prime of x equals 0 for all x, and we're done. Or there's the much more realistic chance that it doesn't equal 0 for all x on the interval, in which case we have a continuous differentiable function over the interval, which means it is bounded, which means that there is a maximum or a minimum somewhere along here, which we can actually generally refer to as an extremum. And then by common sense, or Fermat's theorem if you want to get fancy, this means that at this extremum the derivative, which we know exists, equals 0. Alright, so we're 3 down, 2 to go, on to the Cauchy mean value theorem. Now to prove this, we of course require another theorem, in this case the standard mean value theorem. And what this says is if you have your nice function with all the t's and c's of continuity and differentiability from before, if you have your interval ab, there exists some c in a and b such that f prime of c equals f of b minus f of a over b minus a. And visually what this looks like is taking the line from a f of a to b f of b, which is known as a secant line, and at some point between those two, if you draw a tangent to the curve, it's parallel to that line. Again, this seems fairly intuitive, but things are becoming less and less obvious. Alright, so let's tackle this one. So our secant line has a gradient of f of b minus f of a over b minus a, which is just your standard formula for a gradient. And now if we try and get the equation of that line, given its gradient and the fact it passes through a f of a, we get that y equals f of b minus f of a over b minus a times x minus a plus f of a. Now what we're going to do is define a new function, big F of x, which will be the distance between f of x and our secant line, which as a formula looks like this here. And visually what this looks like is taking our secant line and mapping it to the x-axis, and transforming the entire plane in this manner, so that we end up with something like this. And just looking at this, the next move is clear. We apply Rolle's theorem because our big F is continuous, differentiable, and equals 0 at the two ends. So we consider the derivative of big X, remembering that the a's and b's are just constants. And Rolle's theorem means that there is some c for which big F prime of c equals 0, which means that, ultimately, little f prime of c equals f of b minus f of a over b minus a. Boom, standard MVT done. Now for the Cauchy addition. And the main difference here is that all of a sudden we're dealing with two functions, f of x and g of x. Now for g of x we apply the mean value theorem and say that there exists some r such that g prime of r equals g of b minus g of a over b minus a. And we assume here that g prime of r does not equal 0, and thus g of b minus g of a also doesn't equal 0. Now this is important because now I'm going to ask you to consider this funky function. And our work above tells us we'll have no problem since the denominator is non-zero. But why are we considering this function? Well, that's a great question, and if you find out, please let me know. Nah, I'm only joking, a little bit. Even if this one is harder to visualize in your head than before because we have two functions and we're looking at how they change with respect to each other instead of just some x values, I think it's clear to see that h of x here is entirely analogous to big F of x from before. The only real difference is that b minus a has just become g of b minus g of a, and as a result we don't multiply that by x minus a, instead we just multiply by g of x. Now if we plug in the two ends of our interval, a and b, into h of x, we get this here, and we can multiply f of a by 1 in this clever manner, and then we'll get that the f of a g of a's cancel, yielding finally f of a times g of b minus f of b times g of a over g of b minus g of a. And then with x equals b, it's much the same process. We cancel the f of b g of b's this time, but crucially these two values are equal. So we have the situation where we have an interval ab, where h of a equals h of b, and this means we can get rolling and declare that at some point on this interval, h prime of c is going to equal 0. And so f prime of c equals f of b minus f of a over g of b minus g of a times g prime of c, which, if you recall at the start, we assumed to be non-zero, which implies that f prime of c over g prime of c is f of b minus f of a over g of b minus g of a for some c on the interval from a to b. Alright, and now we have this all done, we can try and finally prove L'Hopital's rule, starting with the classic case where we have 0 over 0. Alright, so we're going to define a as the point where f of a equals g of a equals 0. Now the thing we need is that g prime of x does not equal 0 near x at a. This is the assumption for L'Hopital's rule, and it's almost always true. And then we can pick a suitably small interval a, b, such that g prime of x is either always positive or always negative on this interval, which means that on the interval from a to b, g of x does not equal 0. So what this means for us is that for all values of x in the interval from a to b, we can apply the Cauchy mean value theorem to the interval a to x. Now this is the part where it's important that g of x is non-zero, because if it wasn't, then our denominator, g of x minus g of a, would become 0 minus 0, and we'd be dividing by 0, which means that we'd be turning our indeterminate form into another indeterminate form, which would be entirely useless. But since we know that g of x is not equal to 0, there exists some c from a to x such that f prime of c over g prime of c is f of x minus f of a over g of x minus g of a. And since from before f of a is g of a, which is just 0, we get that f of x over g of x equals f prime of c over g prime of c. So now we can pull out some imprecise moves and consider the limit as x approaches a on both sides. And as x approaches a, our interval gets smaller and smaller, and we just run out of places to stick our values of c, and we end up with the value of c approaching the value of x. They sort of just smush together, and finally we get that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. Alright, and now for the case where f of x and g of x are going to be plus or minus infinity. We start this one by assuming that the limit as x approaches a of f prime of x over g prime of x is equal to some value L. And you may notice that plus sign there showing us that we're taking a one-sided limit. I'm pretty sure the reasoning is identical for the other side. And we then use the epsilon delta definition of a limit, which you may or may not be familiar with, to say that for all epsilon greater than 0, there exists some delta greater than 0, such that L minus epsilon is less than f prime of x over g prime of x, which is less than L plus epsilon, for all x between a and a plus delta. Now, if you're unfamiliar with this notion of a limit, essentially what it tells us is that if you say you're going to vary the input of the function by a certain amount, I can give you the amount that you'd have to vary the output by to account for the variation. Basically, if you nudge the input a little bit, I can nudge the output by a little bit. And what we can now do is set b equal to a plus delta, and adjust delta such that f of x and g of x are continuous and differentiable on the interval a to b, and g of x does not equal 0 for x in a to b. Then, for every x in the interval a to b, we can apply Cauchy's mean value theorem on the interval of x to b, and say that there's a c such that f prime of c over g prime of c is equal to f of b minus f of x over g of b minus g of x, and then given that g of x is not equal to 0 on this interval, we can divide through by it, and then we can rearrange multiplying through by the denominator and minus 1 at the same time, And then we're going to group together these terms and ultimately get f prime of c over g prime of c is equal to f of x over g of x minus r of x. And now look what we've done. We've got an expression relating f of x over g of x and f prime of c over g prime of c, which is almost what we're looking for. We do have to deal with this r of x term, but we'll get back to that in a second. Remember how we had this bound before? Well, we can let x equal c and then use our other formula to get some bounds on f of x over g of x. Okay, so now let's break down that r of x. It's f of b over g of x minus f prime of c g of b over g prime of c g of x. And as x approaches a, g of x approaches infinity. I mean, that's the whole basis of our work, that's why we're doing this. So the first fraction here tends to 0. And since we've assumed that the value of the limit as x approaches a of f prime of x over g prime of x to be L, something non-infinite, this will approach 0 as well. And what I'm going to claim is that we can make delta small enough for the absolute value of r of x to be less than epsilon. So L minus 2 epsilon is less than f of x over g of x, which is less than L plus 2 epsilon. And our value of epsilon is entirely arbitrary, since when we did this limit we picked the value of epsilon first. So we can make this as small as we want, and that's probably not sufficient, but I'm going to call it sufficient to show that the limit as x approaches a of f of x over g of x equals L. And thus, the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. And boom! We have now proved L'Hopital's theorem, which I cannot be bothered to read out in its entirety, so all you're getting is this. Now before I finish up, I do want to give an example of where this is actually useful, because there's no point in making up theorems for theorem's sake if you're never going to use them. The most famous example is, of course, sine of x over x as x approaches 0. This is one of those in the form 0 over 0, but if we apply L'Hopital's rule, we end up with just 1. And then another example would be the limit as x approaches infinity of x squared over e to the x. Now you may have realized that I never did talk about limits to infinity, but it works the same way, I promise, and this time we hit them with 2 L'Hopitals in a row and get that this limit is equal to 0. And thus concludeth the video. I hope you enjoyed, and I hope this showed you why mathematicians are addicted to proving the obvious. Just saying a function has a maximum and a minimum isn't much, but without that we'd never be able to prove any of the cool stuff. Thanks for watching.